Well, thanks, Jason, for the introduction, the very accurate introduction, and it's a pleasure to be here. I've got a few students in LTI, so I'm hearing all the time about the great work being done here, and occasionally having to aggressively recruit my students to come back when they graduate MLT rather than get poached away. So it's really nice to actually meet you, and glad to be here. I'll talk a bit today about sort of one prong of my sort of research agenda, which is sort of focusing on human-in-the-loop learning, and it'll be maybe a talk with some optimism and some sobriety. So I'll talk about it's sort of one of a number of aspects that we address in the lab. So our sort of newly christened approximately correct machine intelligence lab, and these are my PhD students over here. I think Jason painted a pretty accurate picture of what we care about. The way I describe it is that a lot of machine learning focuses really myopically on problems of pattern recognition, and we sort of assume the data, we assume that we're passive observers, and we assume that someone else knows what to do with the outputs of our models after we hand them off. And this sort of widening of scope is the thing that I really care about, this question of where does data come from? So today we'll sort of maybe touches that aspect a little bit. This question of could we be more strategic in the way that we sort of solicit information from the environment? And a lot of our problems, we're also interested in things like causal effects, trying to actually figure out how do you make intelligent decisions based on the data that you've observed, not just how do you predict what would have happened if you're a passive observer and someone else continues to make the decisions the same way they always have. So we're interested in these problems. We're maybe as an application area, we're mostly focused on, I won't talk today about healthcare, but we're mostly focused on applications to healthcare. I think one reason why healthcare is a nice motivating application is that it has like less tolerance for bullshit. So it's harder to get away with the same kind of things that you could use sort of heuristically to guide a recommendation system. And if it goes off the rails and gives horrible recommendations for a few days, we don't really care that much. In the case of healthcare, I think we really have to be on firmer foundations, and it kind of forces us to be a bit more accountable. I guess it's maybe weird that I don't list deep learning here, given that I was probably hired as like deep learning guy. But these days, I kind of view deep learning as a garnish, or I'd say that deep learning plays a role in most, but not all, of the papers that we play. But the reason why I don't think of it as a primary focus is that it's almost never the interesting part. And so it's not to say that there aren't papers that are interesting where deep learning is the interesting part. But I think that very often, I think great, we've got great black box function approximators. Now what? What can we do with it? But the actual parameterization of the like doing brute force architecture search and these kinds of things are not what excites me. But rather say, can we do causal inference better now that we have these models or whatever? In particular, just to give proper credit, I'll talk about a lot of work and won't have time to maybe necessarily do credit attribution for every single idea or experiment, but this line of work in active learning is a result of basically work that started the year before PhD. I was a full-time scientist, or the year before I started as faculty, my last year PhD, I was a full-time scientist at Amazon AI, working with Anima and Nankumar, and we had a bunch of great interns, and a lot of this work grew out of this agenda that we had together in that lab. So it was work with my interns, Ashish Katan, Peiyuan Hu, Yan Yao Shun, my PhD student, Divyansh Kaushik, and some recent work in collaboration with Byron Walls and his PhD student, David Lowell. So in the first part of the talk, I'll talk a bit about active learning and kind of more classical view of active learning and human-in-the-loop learning, where we just think about soliciting labels for examples. And then what I like to talk about more in the second part of the talk is rather than viewing human simply as a data labeling machine, thinking about maybe some more, and not just in active learning, it's not just that we think of humans as a data labeling machine, it's also we paint a cartoon of what that process really looks like. We kind of ignore the hard work of actual crowdsourcing, which is done by people usually who are specialists in crowdsourcing itself. Take a greater look at what's actually involved in soliciting information from people, and dealing with the fact that you can't just say ask people for a question like which one of 10,000 categories from an ontology that you've never encountered before does this example belong to. So what happens in reality is you have to ask people things like yes, no questions and get to the answer that you care about. And if you frame your budget in that sense, in terms of how many questions do I have to ask people, you get to very different sorts of methods and answers than if you just think that I have a human where I just pay some fixed price and they just magically give me the right answer. Also look at the fact that something that crowdsourcing people, so this is because my intern at the time, Ashish Ketan, who's now a scientist at Amazon AI, was actually an expert on crowdsourcing. One of the things, the fundamental problem that they would look at is learning from noisy human judgments, noisy human feedback. In active learning, we often just assume I've got this magic box that I feed in an example and correct label comes out. So thinking about how does contemplating the noise in the act of, in the process of crowdsourcing play a role in how we do active learning, or just how we do machine learning in general, rather than viewing data collection and learning as two separate processes, thinking about how does what we can do with learning inform our choices about how we would sort of aggregate labels together when we're learning from noisy judgments. And the last thing that I'd like to talk about, which we'll get to if I can manage time well, is more recent work about that we call learning the difference that makes a difference, using a technique that we call counterfactually augmented data. So in general, deep learning is successful and powerful in everything. Don't need to convince you of this. There's a number of contributors to success, right? We'd like to think that our algorithms are important. NVIDIA would like us to think that computation is important, and it is. And I say that not just as someone who is gratefully supported by GPUs from NVIDIA, but also, you know, as someone who is dependent upon them for the research that I do. And, you know, perhaps another view is that it's really just the access to large amounts of data that has put us into a regime. So if we were still focusing mostly on data sets with hundreds of thousands of examples, a different set of algorithms would dominate. That part of why deep learning is so dominant now is that we're choosing to focus on a set of problems where they dominate. Like I say, just how hungry are these systems? You know, I think building kind of credible image processing, you know, systems tends to require on the order of millions of images. Speech recognition systems, I think academic systems are trained on tens of thousands of hours of annotated data. I think anyone who's worked in industry would say privately that that's nowhere near what it takes to get something on the scale of like what sort of like Google ASR is doing right now. We have NER data sets that contain hundreds of thousands of examples, and we tend to need something like that to get the performance that's reported. AlphaGo was trained with 19 petasquillion hours of self-play, and our goal, you know, I guess you could think of it as maybe kind of a vacuous goal in that it's maybe just the goal of all learning, as we want more performance for less data, and maybe put simply, that's just the goal of all machine learning, is we want to achieve lower error subject to some kind of constraint on the sample complexity. So, you know, there's a number of kind of related literatures here. One way we can get more bang for the data that we have is if we know something about invariances that hold in the data, we could sort of artificially augment our data to say count for all examples within an invariance class. There's sort of maybe two dominant approaches within that. We could try to build models that have an inductive bias such that they are restricted on account of their inability to sort of see two examples within an equivalence class as different. Or we could just do what we do in the age of deep learning, which is we brute force things by just on every single pass through the model, we just sample another example from, you know, by applying a transformation. There's transfer learning. Sometimes without any labels on new data. So this is typical transfer learning. We assume we're going to fine tune to a small label data set. And one of the problems I work a lot on is domain adaptation, which will not be the focus of this talk. But sometimes we can actually build models that are suitable for some downstream data set, even without any additional labels. And sometimes basically everything we need to know about the downstream data set might be identifiable just given observable unlabeled data from the target distribution, labeled data from the source, and some kind of structural assumption that allows us to relate them to each other. So something like the label shift or covariate shift assumptions. And the focus of this talk will be on active learning. So, you know, the kinds of considerations we need to make generally when deciding, you know, what's appropriate is, you know, do we know of these invariances that we can exploit? What precisely is scarce? So I think active learning, we're often motivated by this idea that it's that the examples are not scarce, but labels are, at least in the kind of classic active learning approach. You know, do we have access to large label data sets for related tasks? If so, then we can maybe try to cast this as something like a transfer learning setup. There are questions about just how large that data set should be and just how related should it be, that are really wide open questions. I think for a long time, even before Bert and Elmo, transfer learning has arguably been like the big success story of deep learning, and the comparatively little attention it got academically is only because we have so little that's interesting to say about it. I think nobody has any kind of coherent idea besides we pre-trained on this and we evaluated on that, and this is what we saw. I don't think anyone has a coherent theory yet that sort of explains why practical models actually transfer the way they do and why this is such a beneficial exercise. But I think if we had anything that we had a shred of like interesting technical insight to say about that gave the kinds of actual performance gains that we get from doing sort of fine-tuning with large data sets, then somebody would win a Turing Award for that. But I think we've just been kind of muted about it, if only because we just are kind of groping around in the dark right now. And what we'll focus on is a setting where, say, we have annotators who we can interactively query to get some labels, right? So just don't want to make this the focus of the talk, but just in terms of data augmentation, standard thing is just we can within an invariant set, we have some set of transformations we can apply. We can apply them, brute force it, and train our model. You say applying a different rotation on every pass through the model, or additive Gaussian noise, or whatever it is that we think our model should be insensitive to. There's slightly more sophisticated things we could do. So in a paper a couple years ago, we showed that we might believe that different examples within the class should not just map onto the same label, but should sort of, as early as possible, get the same representation in the model. And we found that we got significant gains by doing this in speech recognition. So we were able to learn sort of like noise invariant representations, and empirically these tended to generalize much better out of domain when we found ourselves like evaluating on domains where there was, say, background noise, even if it wasn't, and this is just an empirical finding, but often when it was even a very different source of background noise than the one that was used during training for learning the noise invariant representations. And these are significant gains compared to just doing data augmentation. Similar things have been done in computer vision, for example, where people say you should do something like match the logits and not only match the label when you do adversarial training. Again, we talked a little bit about transfer learning as something we could do. I do a lot of work in domain adaptation. So here's an example of if, for example, we believe that there's just some structure, like maybe we believe that the label distribution is shifting over time, but that, say, the class conditional distributions, like what our data looks like conditioned on the label, is not changing over time. It might turn out that actually we don't need any label data for our test environment. What we can do is we can estimate on the fly what is the true target label distribution. We could do this using either like a maximum likelihood approach or a moment matching approach. And then we can use these to apply some correction on the fly that would sort of update our predicted probabilities based on the new label prior. And we actually don't need any kind of interaction because the structural knowledge will actually do all the work for us. So active learning, in sort of the maybe most widely studied or talked about approach, at least in like the ML literature, and this is an image stolen from a nice introductory book by Burr Settles on the topic. I guess it's not stolen because it's credited, but I'm going to be careful. This talk's being recorded. Learning proceeds in the kind of following way, which is that there's a loop where the model is inserted into the annotator is inserted into the learning process in a way where you start off with a pool of unlabeled data. Maybe it's been warm started by labeling some small fraction of it. And then in each iteration, we're going to basically have some kind of acquisition function, some way based on the current model of selecting some unlabeled data from the pool, passing it to the annotator, then getting the newly labeled examples out, adding them to the label training set, updating our model, and then again, continuing this process of now labeling some new data, adding it to the corpus, updating the model. An important thing to note, which is going to come back when we sort of take a critical look at our own work and sort of broadly what's being done in this field, is that you should note that the model here is coupled to the data set that's being collected, right? If you had a different model in the process, or even qualitatively similar model, but you just change the architecture, you change the word embeddings, you change anything, if the acquisition function is dependent upon the sort of partially learned model, or the model learned on the partially annotated data, then what model you're learning actually determines what data set you collect. And this could present problems that we'll talk about later. There's sort of this isn't the only way of thinking about active learning, and I think we'll talk about some other ways of using annotators and thinking about just human-in-the-loop learning more broadly later. But there's sort of a number of setups that are talked about. This is again from Burr's book. There's pool-based learning where you say I start off with some fixed set of unlabeled examples that I have the option of labeling. There's a sort of stream-based alternative where you just say, hey, on the fly, data's passing through, and I have to make a decision at that moment. I guess presumably you don't have to worry about that if you have enough memory. And something that I'm actually very interested in, and I think is sort of maybe a neglected aspect of this, is the idea of Denovo active learning, which is maybe in well, we'll talk in a second, but perhaps in like the best motivated toy cases of active learning, what we're doing actually is Denovo active learning, which is basically where you can synthesize an example on the fly and pass that for annotation.
So in-penning with GANs is fundamental way of being able to do that?
Potentially. So then the question is...
I think the reason people haven't worked on it so much is because it was hard to construct examples that were close to the manifold of real examples, and now we can probably do it.
Right. Or if they are, then it is only still like interpretative and not extrapolative, potentially. So if you want to generate something, if your hope for generating de novo examples is to test out, what would happen, like when we do science, we want to see what would happen in some regime other than the one that we've encountered so far. And one thing that models are very bad at is that these purely associative models, at least we don't have a good sort of theory of extrapolation. So what we're mostly learning is models to generate samples that look like the distribution of things we've already seen, not the distribution of things that we would like to see, but definitely haven't. Right, so is active learning a good idea? The sort of classic example that makes us excited about active learning is you say, let's just say I'm trying to learn a simple thresholding function. I think in Burr's, there's a million versions of this. Every version comes up. Some just are a little bit drier than this. I guess Burr's got a feeling for the common man because the example of you're trying to determine if your fruit is safe to eat or not. It's characterized by some single property. I guess it's like the squishiness of the fruit or something based, I don't know what that is. And the idea that this is a realizable problem. So like there exists, these are actually separable. There exists some threshold where everything above it is not edible and everything below it is, or something like this, or vice versa. And so you say, how many examples would I need if my actual background distribution was uniform on the interval in order to basically find the threshold up to error epsilon? Pack learning says we could do it with roughly 1 over epsilon samples, and there's a question of can we do better? And the answer is yes, we can actually get like an exponential gain in doing this if we just perform binary search. So there's, you say, oh, okay, active learning is great. I have the kind of improvement and sample complexity that one can normally only dream of. On the other hand, if you read some of the sort of more advanced ML literature considering higher dimensional data, extending the theory to the agnostic case, there's some nice papers by Sanjoy Dasgupta and Nina Balkan. Jason knows everything, so he's nodding, but has probably read the papers. You'll see that there's, the story is actually a bit more pessimistic. So it turns out that in general, in agnostic problems, so when there's the classes are not clearly separable and you haven't made any kind of strong assumption about the distribution of the data, sort of in general, their active learning cannot be, just provably cannot do any better than supervised learning. And you'd think that's actually, you might even be afraid of worse than that. It's possible that, in many problems you could do much worse. There's a whole literature on active sampling that's not necessarily in the ML literature, but is, kind of more like in design of experiments where you could think that sort of whenever you do anything that's non-random or non-uniform, you in a sense kind of expose yourself to a worst case scenario. One of these experiments that you see a lot in kind of the literature on the design of experiments is something like maybe I'm just evaluating a function at each of some points, and I could say something like, well, one thing I might think is that one objective would be I want to basically minimize the distance at any point could be from a point that I've already sampled. So you say I want like a space-filling design. I want to choose my point strategically so that you know, the furthest point among the unlabeled spots to something that I've already observed is minimized. So that winds up with doing something that looks like grid sampling. And the problem with that is you actually make your worst case scenario much worse than with random sampling, because you can have like an aliasing effect where you sample like every fixed interval and then actually you've exposed yourself. So like in general, one kind of like meta point I'd make here is that whenever you do active learning, there's a common thread, and I think it relates a little bit to the culture of leaderboard chasing, that we propose a heuristic, we try it on a data set, we report the number, and then we like peace out. But something that you might want to always do when you design an active sampling heuristic, and this will come up in one of the papers, is just think, let's just say I want to screw up my strategy. What is the data set where my active heuristic is going to fail miserably? So sometimes you might come up with a heuristic. For example, if you come up with a heuristic that like an uncertainty heuristic, so I should label the examples I'm uncertain about. If it turns out that there's some part of the sample space where the label is truly given by a coin toss, does that mean that your strategy is going to spend 100% of its time querying examples from that little region versus sort of like moving on and actually sort of exploring the space? So in the conventional active learning approach, so going back to like sort of pool-based active learning for standard kind of machine learning problems, we have a number of questions we have to ask. One is just, what is our acquisition function? How are we going to decide which examples to label at each time? We have a question about how many queries do we want to grab per round? How many examples do we want to sample for querying per round? There's a bit of a trade-off here. Is that if we retrain our model, if sort of each round requires that we retrain our model, then if we sample our examples one at a time, then this might take forever. On the other hand, if we grab a large number of queries, we might grab like redundant queries. It might be that the model just picks 10,000 examples that sort of like all convey the same information. So we have a bit of a trade-off between efficiency versus doing like the pure active learning thing. There's questions from like a deep learning consideration, which just is sort of the environment we're in, that those are usually the models we're working with, of what do we do after each round? Do we fine-tune? Do we train from scratch? Is there some kind of problem that emerges by virtue of the fact that like if you're fine-tuning every round, you've fine-tuned, you've basically applied many, many, many updates on the examples that you collected early and maybe only a small number on the examples that you collected later. And there's one crucial point that we'll return to later, which is that for this stuff to actually be practical, so this active learning, I think, is something that we talk about in the literature much more than we actually do. For this stuff to be practical, we have to get it right the first time, right? Because the very premise of active learning is we have a fixed labeling budget. We have access to many more unlabeled examples than we can afford to label, and therefore we could do something good by being strategic. Rather than labeling all of our data set, which is not an option, or random subset, which is sort of the thing we actually do, we're saying we're going to make a strategic choice. We're going to spend all of our budget in a way that is something other than, you know, uniform sampling. And that means that once we've spent the budget, presumably we're out of money and we can't get any more data. So basically, if we somehow screwed it up and there was a bug in our code and our model updates were going wrong, and therefore our acquisition function was picking the wrong examples, and we wound up with the wrong data set, we're screwed. Because at that point, we've already spent the budget, and we can't go back. So actually, and this is, relates to a paper you'll talk about later. It's a collaboration with Byron Wallace and the student David Lowell, is that we wrote a paper called Practical Obstacles to Training Active Learning, or to deploying active learning in the wild. But basically, this stuff is, I think, actually really important, and it's sort of overlooked in a lot of the papers, where you sort of just presume, even in those very papers, right? I mean, put it this way, how many people here train neural networks, at least sometimes? How many people have ever approached a new problem, trained a neural network, and just got everything to work right the first time? Right, so that I think gives you a sense of like, if that situation, which seems to be the standard situation that you all face every time you deploy a model, means that you wasted your entire annotation budget and now the research project is dead, you know, this is a sort of fundamental obstacle. So a lot of traditional acquisition functions for how you choose which examples to label in the context of active learning are based on some idea of picking the examples that you're most uncertain about. So you have these heuristics that say like least confidence. So I'm going to take my predictive distribution, look at, let's just assume that my decision rule or my prediction is to output the argmax. So I'll basically look at the max and say, how low is the max? Alternative is to say, I'm going to look at maximum entropy. These are the same thing if it's binary classification. They're not the same thing if it's multi-class classification. There's another kind of setup when you have some kind of sort of set of models to compare to each other. There's this approach called Bayesian active learning by disagreement. And the idea here is that if you have a stochastic model or you have a family of models, we could say, for example, if we have parameter uncertainty or something like this, we could say we're going to sample multiple times. So we're going to sample from sort of each member of our ensemble. And we're going to look and basically see, like, what is the consensus prediction? Which prediction gets a plurality of the votes? So they each vote on what the label is. And basically, we'll say that the example we're least confidence in is the one whose prediction has sort of the least consensus. One way of applying Bayesian active learning by disagreement was popularized by a friend, Jaren Gall, who made some argument that we're already training these models. They already use dropout. He makes some argument via some analysis that claims that they are and somehow related to deep Gaussian processes, and comes away with this takeaway that one way that you can get uncertainty estimates from dropout regularized or generally stochastic regularized neural networks is that you can basically sample multiple dropout masks, pass the example through one time for each mask, and then consider basically the predictions upon, you know, the mask contingent predictions to be like the vote. And so then you're going to look. Now, there's a lot of problems that emerge, like if you have a different dropout rate or trained a different number of epochs or any of these different things, you'll get different kinds of uncertainty estimates, and how you actually relate this to you know, any kind of like coherent, you know, accounted for beliefs is a little bit difficult, but this is a heuristic that's sort of popular and used in practice. An alternative, and I'm only going to describe these two, but there's a whole number of additional heuristics that have been used for estimating uncertainty from neural networks, especially a bunch of recent work by Andrew Gordon Wilson, like where they say things like different points along the training trajectory, those weights are the relevant members of the ensemble. In a paper called Weight Uncertainty from DeepMind in 2015, a popular paper, they say the way we'll capture uncertainty in a neural network is that we're going to use, rather than representing each weight as a point estimate with a single parameter, we're going to say that we're going to have a distribution over the value of each weight. They do the kind of obvious, like, simple thing of, let's just say that each weight is an independent Gaussian characterized by two parameters, one the mean, one the variance. And then say that we're gonna have a variational objective. We're gonna tell ourselves that what we're doing is minimizing some divergence between the variational distribution and the true posterior. By the time we've made all of our simplifying assumptions and worked out the math, what we're doing actually looks a lot more like just doing max likelihood with a regularizer. Whether or not you really believe that what we're capturing is uncertainty is, you know, a question that we don't have time for, but I think one worth asking. One thing about the method is that it's become popular in part because it, you know, at least on toy examples, it kind of gives us what we hope to see. When we feed in, for example, data from this segment of some kind of sinusoidal pattern, if you just ensembled over different runs, over different subsets of the data, what you find is that actually the models give you, tend to all extrapolate in the same way as you go off manifold. When you do this weight uncertainty approach and you look off manifold, it seems like you actually do get uncertainty bars that blow up as you move away from the support of the data. There's something that a point that I'd make here is another meta point is that a lot of these applications, these uncertainty generation heuristics, are really heuristic, and they're really loose with like the semantics of what we mean by uncertainty. And one thing, you know, I think worth thinking about is whenever we talk about uncertainty, it's worth asking sort of, it's kind of like whenever you talk about an expectation or you talk about accuracy, you're talking about any of these things, you say with respect to what? When you talk about uncertainty, it's like with respect to what set of things that could change that you are sort of contemplating. A lot of people talk about like terms that are well-known in statistics. I think were popularized in the ML literature by Jaren in a recent paper. He talks about aleatoric versus epistemic uncertainty. Epistemic being that which like disappears as you've seen more and more of the data. Aleatoric being the like intrinsic variability of the label. those aren't the only two. Those are two sources of uncertainty that would exist even if you believed with 100% certainty that the distribution is fixed over time. For example, if you were contemplating the possibility of distribution shifts, you see a lot of people apply that machinery in the context of distribution shift, but in distribution shift, you're encountering a different kind of uncertainty, which is like, what are my beliefs about the stability of the distribution over time, which is not accounted for by either of those two. So, right, we wind up with our objective that basically says make a variational distribution look a bit like the prior, and also, sort of like minimize the negative log likelihood. I first applied these tools kind of heuristically in the context of dialogue policy learning when I was an intern at Microsoft Research in 2016, but it takes a while to publish stuff. So in that case, we said, well, let's do something like Thompson sampling. And so we should choose, we want to choose each action according to the probability that it's the best action. And so we apply these tools. I don't want to get too much into the details, just want to keep up with time. But we say something like at test time, or sort of like as we're running the model, basically what we do is we'll grab a sample of the weights, pass through the inputs, some characterization of the state, and whatever for that sample of the weights was the predicted to be the action with the highest Q value, that's the action that we'll take. And so what we're doing looks like Thompson sampling, but again, like this subtlety of like whether what we're doing is the correct thing. What you really want to do Thompson sampling is you want distribution over Q functions, beliefs over which Q function is the right Q function, the true Q function, like beliefs about which is the Q function corresponding to the optimal policy. That's what you would want to actually do Thompson sampling. What we're doing here is actually, we're capturing parameter uncertainty, but it's parameter uncertainty for the value of not the Q function, like God's Q function, but the Q function corresponding to the current policy that collected the data that we have, right? So they're not the same thing, but it's easy to convince ourselves that we're doing something like the right thing when we get results that are much better than sort of the status quo at the time, which in this case we did. So, we had this machinery for generating something that we call an uncertainty estimate, and we're interested just sort of heuristically initially in saying, what happens if we go at some sort of data-hungry task like NER, this particular NER passage that I found. I just wanted some eye candy for NER to put on the slide, and for some reason, everything that like came up on Google image search that day for NER that sort of looked like a color-coded tag corpus either mentioned Trump or Hitler, so I went with Trump, but apologies if anyone got triggered. We looked at and said, sort of, can we improve upon, or can we get the performance? So, I think we had like 625,000 utterances, I think, and onto notes we were interested. Could we get something like the best reported performance of the best deep learning sort of NER systems using only a small fraction of the data if we were to collect it, using an active learning heuristic? So one thing is we need many, many rounds of retraining. So we did some modeling improvements. We went through our NER pipeline, and we basically found every single component of it that we could get away with replacing sort of LSTMs with convolutions to make it as fast as possible. So we got a significant speed up by turning our word beddings into convolutions, our sentence embeddings into convolutions, and the only LSTM that was left was in the tag decoder. And we apply greedy decoding here. And we look at a couple different active learning heuristics. On one hand, we looked at doing Bayesian active learning by disagreement using the weight uncertainty and using the dropout heuristic. We also looked at just doing the standard thing of just looking at the sort of log probability assigned to the prediction. And one problem there is that when you're doing NER versus doing just multi-class classification, that you're sort of always going to assign lower probability to the longer sentences if you're looking at the probability of the tag sequence. So we just normalized the log probabilities by the length because we just didn't. And there's sort of two reasons why we do this. One is that we're sort of accounting. It seems like a more reasonable. And this is, I think, actually a little debatable, but it seems unreasonable to account for the cost of annotation as the same for like a 2-word sentence and for a 20-word sentence. It's probably also unreasonable to account for to just look at the cost of annotation in terms of words, because it's probably some context switching cost when you, like my guess is that doing 10 two-word utterances or 10 two-word sentences is more expensive than doing 120-word, but we wanted to think about costs in terms of the per word cost as the cost of labor, not the per sentence cost. And so we went and we applied these tools, and eventually we found, interestingly, that with about 25% of the amount of data, so this isn't the kind of like exponential gain that you get from doing, say, like solving our simple, which is the safe fruit thresholding problem, but still we get what looks like basically like a 4x reduction in sample complexity. So this is the IID model right here. You just labeling your examples randomly. And we get is with 25% of the samples, we get 99% of the performance. So we were pretty satisfied with ourselves, you know, in the way that I think everyone is when you get your experiment to work. But there's also some serious problems here. Yeah.
Just to clarify, so when you do the active sampling on the sentence, you have the boundaries where you ask the annotator to say for this span what is the label, or we just give the whole sentence, and they have to.
Right, we're giving them. Right, we have sentences. We're feeding them, and this is simulated, right? So this is I think another big problem in a lot of literature. What we're doing is we're simulating active learning. So we have this sentence. We're imagining that we sent it to an annotator and got back the true label that is like the label that is in the corpus. So there's a few things that are wrong with this experiment that should maybe make us not so excited just yet. So I'd invite you to like attack our work. Yeah. Right, this is over rounds of active learning. So like we've run it start to finish and seen, so every point should basically, when you get to 100% of the data, should basically be the same up to like noise. I think we never get to 1%, because I think actually like there's some minimum amount. Right, so what seed you make can make a big difference, and in a lot of our experiments, we've actually looked at this source of variance. In this exact plot from 4 years ago, I'm not. No, not here. I think this is just a particular run. But there's, I think, really, I think those are all good points. There's also a lot of grave problems here. One is that we've tried a bunch of heuristics in the process of like formulating this research agenda, and eventually we've settled on something that seems to work. But so one, we've tried lots of things, and then we're retrospectively finding something that did better than IID on a particular data set. That's not necessarily an assurance that in the future, given a new data set, like in the new data set, we don't get to try. It's not like supervised learning is the kindest, you know, most forgiving problem you'll ever encounter, because it truly lets you, as long as you have a big validation set, you could try all the models, and you could pick the one that did best on validation, you could deploy it. But in this case, we would not have the luxury of trying lots of things and gaining intuitions where our intuitions could potentially be married to this data set, and then retroactively saying, oh, well, you know, now that I've tried 10 things, one of them did much better than IID. So what we really need is something that would do better than IID on new data set. Another thing is that we're using architectures where the very architectures themselves are learned to be good at this standard problem, where most of our knowledge for what constitutes a good NER architecture is coming from one of two data sets, right? So same thing when we do these experiments on like CFAR 10, CFAR 100 ImageNet data, we're doing it using models that themselves are already reflecting knowledge that we only would have had by virtue of actually having all of the labels.
There's another sort of issue, I think this relates to what I was asking earlier. Let's say you start with whatever 3, 5%, whatever the starting point is, right? Now you could have had a very bad starting set, and you could go completely off the rails.
Sure.
But you know you're in the 70-something range, and that's where you should be, because you've worked on this particular corpus.
Right, you know what is...
You know what in other words, how does one do this in real life?
Right, in real life,
If
you're getting 40% accuracy, does that mean you're amazing or that you're terrible? Great questions. And I think that there's not always a great answer. Right, so a problem is that, you know, it sounds great on paper, but what we're doing is not really indicative of what you would really need to deploy this stuff. It paints a cartoonish picture of annotation. It's got these sort of like almost like a selection or survivorship bias that like the model that gets through is pronounced as the winner, but it's not evaluated in the way it should be on future data. In reality, you're right, we can't run 4 strategies and retrospectively pronounce a winner. We can't use the full set of labels to pick the architecture, pick the hyperparameters, pick the learning rate, do all this kind of stuff. And again, right, what if we just have a bug in our code and the whole thing goes off the rails? And these are just a few of the questions that we identified originally. So I just have a little bit of a contrarian streak, so I was happy to throw my own work under the bus, and I got together with a master's student who's a really strong engineer when I first got to CMU, Aditya Siddhant, and we said, you know what, let's think about it this way. Like, active learning is often simulated on one task with 1 or 2 data sets with 1 model, and then this pattern of throwing, you know, kind of the kitchen sink at it. Let's say, let's basically pick like a large menu of tasks. For every task, let's pick multiple data sets. For every task and data set, let's pick multiple models. For every task, data set, and model, let's run across multiple random seeds to address that concern that maybe we just got lucky and got a good seed on a particular run, and that's all that we're finding. For every task, data set, model, and random seed, let's choose our hyperparameters only using the warm start data that is available. So that's the data that's going to determine the number of layers, the number of nodes, the learning rate, whatever. And what I was expecting to see is basically just like a giant, just kind of like drop a bomb on active learning and say it doesn't work, let's move on. And surprisingly, but the hope would be like, okay, in order for an approach to be good, you'd like to think that it would show a consistent gain across data sets, problems, architecture types, random seeds, whatever, that we would see across all of these that there was a model that just consistently performed better than IID. And interestingly, we actually found that and one kind of cool thing is that on, I think it's this model here, the CNN, TNN, LSTM, the same setup that we had done in the previous paper, we found that indeed similar findings to what we had found in the previous paper. So at least that's reassuring. Like that was, whether or not you believe that it's actually applicable, at least like we reproduced that result. And we also found that, the bald and the sort of classic uncertainty sampling approaches perform similarly well as we had seen in the previous paper. But if we looked across many different models, many different data sets, many architectures, whatever, we actually found that bald did much better than the classic uncertainty sampling. And so our kind of takeaway from there is, we were sort of like surprised to report that maybe if you can get over this hump of actually getting everything right the first time, there maybe is some kind of potential story here that bald might actually, active learning guided by this bald heuristic, at least on like natural data sets, might be okay. Sort of in related work, and this is work that was ultimately published under the title IDM-NLP. I should fix the slide. With Byron Wallace and David Lowe, we addressed sort of different questions. So I mentioned earlier that the data set that you collect via active learning is coupled to the model that you use to collect that data. So one problem that we asked immediately is, well, what's got a longer shelf life, data or models? And in my experience, it's usually data has a longer shelf life and the models change faster. And so one question that we started asking, and this just kind of emerged from like a conversation that Byron and I had at MLHC, was we started thinking, well, if the data set's coupled to the model and the model's got a longer shelf, or the data's got a longer shelf life than the model, what happens if I use like a certain model, we'll call it like the acquisition model, to collect the data? The data is now coupled to the acquisition model, and then somebody reports that it's not Elmo, it's BERT that we all need to use, and then I go out and I use whatever's like the latest fashionable model that sort of seems in general to get better performance. Do I get a benefit? Do I still get a benefit over IID sampling by using the actively acquired data set from the wrong model on the new model? And sort of two kind of disappointing things happen here. One is that we often find this kind of thing where you do a little bit better than IID if you use the native model, but you do worse if you are applying the data set that was actively acquired with a different model, so with like a foreign model. You will often do worse than IID learning. But another problem we tried to do a similarly large-scale set of experiments to what I had done with Aditya, but implementing everything from scratch. So David was using his own code base, and we tried to do a similarly comprehensive set of experiments just investigating this transfer question. And the weirdest thing is that in this process of putting together this 2x2, this matrix, not 2x2, but this model by model acquisition successor model matrix, all the diagonal entries there are like what you should get from vanilla active learning. And two things happened. One, we found you did much worse when you used foreign data versus native data. But the more troubling thing is we found even the diagonal entry lines weren't appreciably better than IID learning. So it's like, okay, we had this other, we had this in the first paper that says active learning works. A second paper that showed almost exact results on the same configuration and pretty positive results across many data sets and many configurations. Now this other paper where we're doing our best job to replicate things. We sort of have honest intention. If anything, we have a bias to replicate things because we don't want to invalidate our own work. And what we find is we can't get better performance for active learning than IID sampling. So we rack our brains. We say, are we using the same architecture? Yes. Same learning rate? Yes. Or setting the learning rate, I should say, according to the same protocol? Yes. Same data sets? Yes. Same tasks? Yes. So what is the difference? After like weeks or months of like just pulling our hair out, what we find is that the difference is something that seemingly shouldn't have anything to do with this, is that we're using different word embeddings. So use like glove versus word2vec, and this made a big difference. And I think this should like scare us all about this way of doing things, that we have a set of findings that, is we even, despite our best efforts to try to investigate all these different axes of variation, can sort of get unraveled by something seemingly unrelated. This should give us some pause, So this is sort of like one line of work, and I leave it as I think there's still interesting questions, but I think we need to think in maybe a more principled way about what is the structure of the data that should actually make active learning interesting or possible. I think we need to think maybe a little bit more deeply about what is the relevant notion of uncertainty here. But the sort of like mixed story, at least for this line of work right now, is I think that it's still very much mixed. I think it's possible that people will come out with much better acquisition strategies that'll work. It'll be so much more of a slam dunk that we won't worry about these small differences. But I think it's also possible that, just getting this stuff to work in a way where we should feel comfortable about running it in the wild is, still very much in a kind of dubious state. So then, partly maybe owing to some frustration over just like this classic active learning setup, also, maybe perhaps another kind of limitation of this whole thing is that we paint a cartoonish picture of what annotation looks like. We just say, I send the annotation, I send the example, I get back the annotation, it is correct, we move on. And that's not actually what crowdsourcing looks like. What crowdsourcing actually looks like is you set up these complicated pipelines for generating data, for getting it annotated, for aggregating predictions across multiple noisy annotators. And we started thinking more deeply about can we dive deeper into what that interaction actually looks like and think about that process more seriously. And this motivated some work that I did with a different intern at Amazon, which is called Active Learning with Partial Feedback, which was published at, that's a lie, it was ICLR 2019. But there was a gestation period for the work, so I forgot which year. So what we did here is we thought, traditional active learning papers just sort of ignore like how the sausage gets made. They say, here's the example, give me the label. But you can't just say, here's this isn't just like, give me the label is not the atomic operation of crowdsourcing, right? So actually annotation requires asking simpler and often binary questions, right? Like, does this image contain a dog? And the relevant notion of cost here in terms of our interaction mechanism should be the number of queries, not the number of examples that we want to annotate. So does anyone know how ImageNet was created? Anybody read the paper? 2009? How? So that's part of it. So what do they do with the WordNet categories? Right. So what they did is they took, it's correct. They took the ontology of a set of items that they wanted to label. They took them. They used Google image search to create a list of candidate images for each category, and then they asked people basically just binary questions. So they got lucky that sort of like we were addressing a problem where you were able to get a good set of candidate examples that was a high enough hit rate that we just needed to ask people yes, no, is this actually a member of the category? We just needed to verify. And so they asked people, and they actually had like multiple users for every item. Yes, no, is this the is this a Persian cat, or is this a Burmese cat, or is this whatever? And then the people would answer, and then they would sort of aggregate these examples, and there's lots of literature on how to do this. The most naive thing to do is majority vote. The active learning literature has produced some more elegant things that you could do. Sorry, the crowdsourcing literature, for example, maybe the most famous algorithm here is the Dawid-Skeen algorithm, where you would go back and forth, and you would basically, based on how much, you would assume that the majority was right. Then based on who disagreed with the majority, you would infer the worker confusion matrices. Then based on the worker confusion matrices, you would go back and re-estimate what you think the right labels are. So maybe if you decided that, 2 annotators said not a cat and one of them said yes, but after going through the first iteration, you've decided that that one worker is much more reliable than the other 2, maybe you take their vote and not the majority. So the part we focused on here is just this question of, you only have binary feedback, what could you do? And so we started thinking this as, if you didn't have the candidates, if you just had images and you knew that they belonged to a hierarchy like an ImageNet, you could think of this as a kind of 20 questions type situation where we have these sort of leaf nodes on this ontology, which are the base labels, but then we actually have these internal nodes, which are not the labels that we care about, but they are the, like domestic animal, like animal versus plant, domestic animal versus wild animal, dog versus cat, and then, at the leaf, maybe you'd have golden retriever versus labradoodle or whatever monsters they're creating these days. So, the naive thing to do, what you would do actually, I think the heuristic that gives you some approximation guarantee, if you had labels and probabilities assigned to them, if you had a uniform distribution, I think the algorithm for just pure 20 questions would be that you should just choose the question at any given time that splits the mass most evenly between, based on your current expectations of what the answer would be between the 2 sides. Once they tell you that the answer is on one side, you set all the others to 0, and now you ask the next question. It's called binary splitting. So we're thinking about basically, if you had to ask these binary questions, we could think about active learning now, not just as a question of choosing an example to get a label for, but rather now each query is a tuple. It's an example class pair, where the class is could potentially be one of the leaf nodes that you care about, but it could also potentially be like an internal node in the hierarchy. Is it okay if we go to 105? Cool. All right, cool. Right, so then the annotator will give us binary feedback, and so we have a few parts. One is, now we have a kind of more complicated structure where we want to choose a query, which is we're not just choosing examples, but we're choosing these tuples, choosing this example class tuple. And the next part is that after we ask a question, it's like after we say, is this image depicting a dog, what we have left is a partial label. We've ruled out some classes, we have some others. And when we apply our update, there's a question of just, do we keep going on one example, basically until we get to the exact label for that example and then move on? Or can we just move on right away and just choose like the next best question? In which case what we're left with is a set of partial labels, and when we update our model, we need a way to update our models based on the partial labels. So we could think of our goals from one of 2 perspectives. One is we want the best possible classifier subject to a fixed budget. And the other side is we want to annotate a data set with the fewest possible queries. So we look at a few different sample strategies. One of the most natural things is sort of the expected information gain. So based on our current beliefs, based on the current conditional probabilities assigned by the model to each of the classes, which question do we, based on what we expect, based on our current beliefs, the distribution of answers might be, will in expectation reduce the entropy of the predictive distribution the most? There's also a few kind of simple heuristics, we could just say, let's just ask the question that we think is expected to result in eliminating the most possible classes. So over all examples, over all questions we can ask, which one in expectation will eliminate the most classes? Or, and this one is going to focus on examples maybe where we know the least about them, because then we have the most classes to rule out. The other possibility, we could ask this question of expected number of remaining classes. So in this case, we're actually saying, I want to drill down to exact labels as quickly as possible. So I want to ask the question that I think is most likely to get me really close to or to get an exact label as soon as possible. So this one's going to focus on trimming off a mass of categories from the uncertain examples that we don't know anything about, whereas this one's going to focus on labels where basically we're really close to getting an exact label sooner. And so we find, so we have a few different steps. We have this regular active learning, which in this case kind of confirms our sort of previous dubious finding that it doesn't do that much better by either conventional heuristic than baseline IID learning in terms of accuracy subject to the questions. The questions like the number of binary kind of answers that we needed. We have active questions, which is we basically choose the questions, we choose the examples IID, but then we choose which question to ask about them according to the heuristic. And we have active learning with partial feedback, which is, this is kind of interesting, and this seems to do much better than active questions, even though active learning by itself does not give much of a gain. So basically, here, active learning with partial feedback is the complete setup of we're choosing both which example and which class to query about that example. So the next step we looked at was we looked at learning from, so the paper is called Learning from Noisy Singly Labeled Data, but while this problem addressed the question of like that you don't get to just ask for a class label, you have to ask these smaller atomic questions. What we focused on here was the fact that annotators are noisy. So we focused on that aspect of the problem. So we still allow them to give us an exact label. To give us a leaf label. But we focus on dealing with worker noise because that's actually what happens. So one thing that we're interested in is, so normally crowdsourcing happens first, and we just don't look at what's happening there. Then we get the data, and then we do machine learning on it. And we're interested in saying, could we do a better job of crowdsourcing if we had a model in the loop? And could we do a better job of machine learning if we did our crowdsourcing with the idea that the goal was to train models downstream? Among other questions, people, most of the time when you grab a machine learning data set, you don't ask questions, or very often I think, I won't blame you, I'll blame myself. Don't ask questions like how many annotators were queried before they aggregated the labels. Did they ask 7 people? Did they ask 9 people? Did they ask 3 people? Did they ask 1 person, right? But normally it's multiple people. And we talked before about how there's this naive baseline of majority vote, and we could do better with EM. And when we looked at it, say, well, you have this trade-off now. If I have a fixed labeling budget and I have an unlimited resource, is it better to have 200,000 examples that are labeled 5 times each, or to have 1 million examples that are labeled 1 time each? And the problem is that if you label examples 1 time each, on one hand, it kind of seems like maybe you just want to get as many examples labeled as much as possible, because there's going to be diminishing returns in how much you learn about each example as you continue to ask queries about the same example. The problem with this is that classic crowdsourcing algorithms like Dawid's they break down if you only have 1 label per example, because what happens is they just decide all the workers are perfect. So say we want the benefits of doing crowdsourcing algorithms, but we still want to be able to just label once and move on. What can we do? So we came with an approach which basically uses the modeling in the context of the crowdsourcing. And the idea is to say, let's have 1 label per worker. But what we're going to do is, rather than looking at saying how many times does a worker disagree with a consensus, we don't have a consensus for each item because we only have 1 worker labeling it. And standard EM stuff is feature agnostic. So what we're going to do instead is we're going to use our model as a stand-in for a consensus. So what we're going to do is basically train our neural network based on the initial noisy labels. Then we're going to look at how much does each worker disagree with the neural network. And some will agree with it very often, some will disagree. And the idea basically is that we pretend that the neural network is correct, and we treat workers as wrong when they disagree with the neural network. We use this to estimate worker confusion matrices. Then we take the worker confusion matrices, and we use this to formulate an objective that basically says, okay, with probability 60% this is the right answer, and probability 20% this is the right answer, and 10% that's the right answer. We relearn under this probability-weighted, not in the standard cross-entry, but under this probability-weighted objective. And then now we have a new model that comes out, and we could use that new model to re-estimate the confusion matrices. And we could do this instead of judging workers against consensus, we judge workers against model. And when we do this, one thing that's interesting that we find is that basically and this is when we have a fixed annotation budget, we find very often that the best performance comes using very small and often just a single label. So we often find that label once and move on is often actually the best that we could do.
When you do this, then let's say determine that a particular label is unreliable, you throw away every label, because they label only 1 example each, so you don't know what to do with it.
No, it's the worker. you basically are weighting the objective. So it's as if.
You're weighting the objective.
So it's like if the worker is unreliable, like if the worker says it's a dog, but I know when this worker says it's a dog, there's a 40% probability it's a dog, and there's a 30% probability it's an ostrich, and whatever. It's just that I have an objective that now captures my beliefs over what the class is, given that the worker said that it belongs to a certain class. And the final thing that I'm excited about here, and this is where I'll end, all right, is, and something I guess we talked about a little bit earlier, Jason, is this idea that, there's a lot of talk about models learning spurious correlations, bad correlations, bias, superficial statistics, but a lot of this talk is completely like kind of floating in this like technically unanchored space where these terms have no meaning in the language of statistical prediction. And so the problem is like we have a kind of, it's kind of like the way like Pearl talks about like probabilists trying to come up with ways of defining causality without actually adding like a missing operator to the language, is that people are just using the same tool, just saying, well, let's solve it using regularization. But they're not actually thinking about even, are we asking a question that's identifiable from the observed data that we have? So one thing that I'm really excited about is this idea of, can we use humans in the loop to actually inject structural knowledge even when, the observational data might not be sufficient. So in this case, we formulate these questions about what is spurious. Spuriousness there's the notion of spuriousness of like, I have a finding that only happens because my sample is too small. But that's usually not what people are talking about here. Usually what people mean is there's a real correlation, but it's not the one you want. So our idea here is that we can cast this in the language of causality is by thinking that sort of a spurious correlation is one that owes to common cause, but is not actually part of the causal structure. So the part of, the spans that matter are the ones that need to be intervened upon to change the applicability of a label. So what we do here is we use human annotators not to give us labels, but to edit documents. And the idea is that in so doing, having the humans be actually like editors versus annotators, they can actually reveal some knowledge that is not contained in the observational data alone, or fundamentally might be unidentifiable. So we have this annotation set up, and basically the idea is that you give them an original review, you give them an original label, and then what you give them is the same review pre-populated in an editable text box, like down here, and next to it we assign a counterfactual label. And their goal is to edit the review so that it agrees with the counterfactual label, it's internally consistent, and that they make no gratuitous edits. That they're told to basically don't change things that don't need to change to make the label semantically apply. You think of it as like kind of a sort of like least action principle here. So we do some qualitative analysis of what you find, but just the takeaway, and this is where we'll end, is that if you train a TF-IDF model on the original data, you find that words like great and fun and excellent appear as very positive words that have high positive coefficient, words like bad and worse and boring are negative, but you also have like romantic and romance is very positive words, and horror is a very negative word. And these are words that we might think of as spuriously correlated, but in the sense that you can have a great horror film, and there's no reason semantically why you can't. Like, for example, anything made by Jordan Peele. So if you train the model on the counterfactually revised data, what happens is that these words stay as positive words, but actually romantic and romance and horror flip. Horror becomes a super positive word, and romance becomes a super negative word. And the reason why is because all those documents that had horror were originally negative. They're all now positive, but they still contain the word horror. So the human has revealed something that might not have even been obvious or even identifiable from the observational data alone, which is that this is not the word that needs to be intervened. So by virtue of what they do versus don't intervene upon, they've revealed something to us. This is, work with a huge amount of work to maintain a workforce of like 1,000 editors by my student Divyan Kaushik. And ultimately, when you train on the whole data set together, the original and the revised, these words actually fall out of the high sort of coefficient features altogether. And similarly, you can see that when you train a model on one data set and then evaluate on the other, you get from sort of like great performance to bad performance, and vice versa. When you train on revised and evaluate on the first, when you train on them all together, you lose just a tiny bit of accuracy owing to not relying on sort of like spurious signal, but surprisingly small. You basically perform well, in both settings. So, and then this is purely empirical, but we also find that if you then take the model trained on the counterfactually augmented data, this is on IMDb data, and you look outside and look at Amazon reviews, look at semi-val data, which is Twitter, and look at Yelp reviews, across all of them, the models trained on the counterfactually augmented data actually seem to perform better. So this is, obviously there's all kinds of weird out-of-domain things going on, but I think those results are exploratory but suggestive that there's something interesting in this line of direction. I apologize I didn't get to spend that much time on it, but I think it's the kind of line of this work that I'm actually the most excited about right now. So anyway, please stay in touch. These are the papers we talked about, and thanks for the indulgence in going a couple minutes past.
So I should have mentioned in my introduction that Zach has lots of interesting blog posts and even a textbook written in Jupyter on deep learning,
So deep learning is a condiment, It's like, it's just.
Gotta learn it somewhere.
Yeah, it's like, I think it's like we all use SGD, but we don't dance about it. Or I think that that function fitting is becoming that kind of thing. I don't know.
So we should probably break at this point because I know people have to get to class in the evening. But if you want to talk to Zach, I think he'll be up here. We'll talk about it.
Awesome. Thanks.